Welcome to the Merlin and Metro News Network. Our program today begins our in-depth look at the electrical system. Now, we'll talk about the bus system that is used to distribute power to other systems on the aircraft. And finally, we'll cover the various indicating and monitoring systems that are used to control and protect the electrical power supply system. During our next 4 programs, we'll be discussing direct current or DC power only. Now, for those of you with prior Merlin and Metro experience, you probably know that there is also an alternating current or AC system installed on the aircraft. Now, we'll be covering that system in a later program. For the time being, all of our discussion about the electrical system will be on DC power only. So get comfortable and sit back and let's roll the first program.
In an earlier program, we said that almost every system on the Merlin and Metro uses electricity to perform part of its operation. Since there are a lot of systems on the Merlin and Metro, so is there the necessity for lots of electrical power. More power is needed than could be provided by batteries alone. That's why engine-driven generators are used to provide most of the power used on the aircraft. Before we begin our discussion, let's cover some electrical basics. Since most mechanics seem to have some amount of aversion to electricity, we're going to cover these principles in their entirety without using an electrical circuit. Once again, we'll use water. Let's start with a means to put water under pressure, a reservoir, and a pump. So that we can determine what is going on, we'll install a flow meter to measure how much water is flowing through the system, and a pressure gauge to tell us the water pressure being put out by the pump. We'll also assume that we have some way of varying the output of the pump. Just outside of our source, we'll install a shut-off valve so that we can stop, start, or vary the flow of water. Connected to the shut-off valve is a feeder line, which supplies the consumer in the house. We've also installed a flow meter outside of the house, so we can determine how much water our consumer is using. If we start the pump running, pressure will build in the feeder line. If the consumer opens a hydrant in his house, water will flow through the feeder line. Eventually, this water will return to the reservoir, either through evaporation and rain, or after treatment through a sewage system. In this example, the return path is less important than the water being supplied. Nevertheless, a circuit is completed. If we check the flow meter at the reservoir and the flow meter at the consumer's house, they should read exactly the same. The only way they could indicate differently is if there is a leak in the feeder line. We now check the pressure of our pump. If we increase the pressure, we will find that the flow to the consumer's home will increase. If we decrease the pressure, less flow will occur. If we begin closing the shutoff valve, we will also decrease the flow to the consumer. Now let's add another consumer. By adding another consumer after the first, we have created an interesting dilemma. The second consumer is now totally dependent on the first consumer to receive any water flow. The second consumer would therefore be connected to the system as shown. In this fashion, consumer number 2 has independent access to the water system, regardless of whether consumer number 1 is using any water or not. Likewise, consumer number 3 could be added, and so forth. If we read each of the flow meters and add them up, their total must agree with the flow meter at the reservoir. If you're not lost at this point, you now understand most of the major electrical principles needed to troubleshoot and repair the systems of this aircraft. Now let's start again, using electrical symbols and terminology. We have 2 sources of electrical power on board the aircraft, the batteries and the generators. The generators are almost identical in function to the pump in our example. The batteries are more like water towers. A water tower can supply water under pressure until it's empty, and then it has to be filled up again. Batteries can supply electricity until they're empty, then they have to be filled up again. Instead of a flow meter, we use an ammeter, because that's what amps means, the amount of electric current actually flowing through the system. Instead of a pressure gauge, we use a voltmeter, because that's what volts are, the amount of pressure there is to push electric current through the system. Our shutoff valve is a switch or a relay. Instead of a feeder line, we have a feeder wire. Our consumer could be a motor, a light, or other electrical device. Electric current returns to the source through the aircraft structure. If we compare the amount of amps flowing through the consumer, we find it must equal those flowing through the source. If we increase the voltage, more amps will flow. If we decrease the voltage, fewer amps will flow. In our water example, the shutoff valve could also vary the water flow. In our electrical circuit, we use devices called resistors to vary the flow. A fixed resistor will decrease the flow by a fixed amount. A variable resistor will allow us to vary the electrical flow because it is mechanically adjustable. There's one other electrical principle that can be explained at this time. Earlier we talked about how the consumers could be hooked to the feeder line, whether each house had its own connection to the supply, or whether one house was dependent on the other for its supply. In an electrical circuit, these differences are referred to as series and parallel. As shown on the screen, these houses are connected in series, these houses are connected in parallel. Replacing the houses with electrical loads, say a light, a motor, and a relay, we have a typical parallel circuit that might be used in the aircraft. Notice that each component is dependent upon the source of electrical power and the feeder line, but none is dependent upon the other. Suppose we change the circuit as shown. Now the relay and the light are connected in series. The light cannot illuminate unless the relay is closed. Suppose we add the motor back to the circuit, say here. Now the motor and the light are connected in series with the relay, but they're connected in parallel with each other. In our previous program, we discussed something called equivalent paths. Usually such a path is parallel. Consider the simple circuit on the screen. Let's say the light does not illuminate. What would be the most immediate course of action? If the motor and the light are connected in parallel, then we know that their source of power is the same. If we check the motor and find that it is operating, then it's a pretty safe bet this part of the circuit is operating properly, and that we should concentrate our troubleshooting in this part of the circuit.
Well, are you still with us? You know, most of those electrical terms and theories are actually named after real people. An Italian physicist and count named Alessandro Volta was where the term volt came from, while a French chemist named André Ampère is where the term amps came from. A German physicist named George Simon Ohm figured out the relationship between amps and volts, and that's how Ohm's law came about. Back in the 1700s, another well-known historical figure was the first to recognize that electricity had a positive and negative side. He figured that electricity probably flowed in one direction or the other, but that we'd never be able to figure out which way. So he guessed that it was probably from positive to negative. Well, with the modern technology of today, we've been able to discover that technically he was wrong. The actual electron flow is from negative to positive. But since so many people have already learned it the other way, from positive to negative, wiring diagrams are drawn this way, and the so-called conventional flow of electricity is taught in schools and used in these programs. For troubleshooting and understanding purposes, it really doesn't make any difference which way electrons flow. Oh, and the well-known historical figure that guessed wrong? Benjamin Franklin. Maybe that's why Ben didn't get any electrical terms named after him. Now, let's return to our program and begin discussing the power distribution system itself.
The electrical power and distribution system are shown in this simplified schematic. Power sources are the batteries, generators, and auxiliary power unit connection. Each of these sources feeds a bus system that in turn distributes power to the other systems of the aircraft. Three major buses are used: the left and right essential bus and the non-essential bus. Each bus has a rated maximum current that it may supply. Current limiters are used as fuses to prevent each bus from drawing too much current. If the load applied to the bus exceeds the rating of the current limiter, the limiter will burn in two, thus disconnecting the bus from the source of power. There's also a switch in line with the bus current limiters that allows the pilot to manually connect or disconnect each bus to the power system. The major electrical power sources on the Merlin and Metro are the batteries and engine-driven generators. Each of the sources provides direct current or DC power. The batteries used in the Merlin and Metro series are nickel-cadmium. This name is derived from the metals that make up the cells of the batteries. Nickel and cadmium are expensive metals to use in batteries, but they allow the battery to store a tremendous amount of electrical power for their weight. And remember that word store, because that's exactly what the batteries do. They store, not produce electrical power. The typical batteries used in the Merlin and Metro series are typically in the 25 amp-hour range. This means the battery could supply 5 amps for 5 hours or 25 amps for 1 hour. The battery can therefore store this much electricity. There is, however, one phenomenon associated with nickel-cadmium batteries that require extra circuitry to be necessary: thermal runaway. When the battery is being charged, it becomes a load on the electrical sources that are charging it. Normally, as the battery charges, the internal resistance within the battery will increase. As the battery becomes more fully charged, the resistance increases and the current decreases. When fully charged, the battery will allow practically no electrical flow. Suppose, however, the resistance in the battery were to decrease as it charges. More and more electricity, more electrical power will be pumped into the battery with only a limited storage space. Obviously, this power has to go somewhere, and it does. It turns into heat. If this action were to continue, significant damage to the aircraft structure could occur. Circuitry is required by the FAA to sense thermal runaway and warn the pilot. The other major source of power on board the aircraft is the engine-driven starter generators. The generators are 300 amp units. Each is driven by the respective engine. We'll discuss the generators in more detail in our next program. The final source of electrical power is the auxiliary power unit receptacle. Obviously, for ground use only, the APU provides power to the bus when the battery switches are in the on position.
For some of you viewing this program, this may be your first exposure to detailed electrical theory, and you may want to know more. Now, it's not the purpose of these programs to teach you detailed electrical theory, but it is easy enough to learn on your own if you desire. There are usually local trade schools and community colleges that have courses in electricity, as well as numerous correspondence courses. Now, if you'd just like to read a little more on your own, there are literally hundreds of books published. Now, we made a trip to the local library and picked up a few example purposes. Now, this is one book on an entire series by Hayden. It starts out very simply and really makes no assumptions about your prior electrical knowledge. Here's a book called Basic Electricity. See if you can get this on the camera. Okay? It's really a high school level textbook that has good practical emphasis. Here's a very simple explanation of how electricity is used to create magnetism. And here's a picture of a relay. Almost looks like the old de-ice boot relay with the cover taken off. Browse through the library's selection and pick a book that feels comfortable to you to read at your level of knowledge. The Bible, if you will, for aircraft electricity is right here. Probably more A&P mechanics have started out with Electricity and Electronics for Aerospace Vehicles by Northrop Institute of Technology than any other book. Now, this is my copy, so it's old and slightly beat up, but it's still an excellent reference. Now let's go back to our program.
The Merlin and Metro series of aircraft use multiple wires to carry the high currents produced by the batteries and generators. Several smaller wires, rather than one large wire, are used to allow tighter routing of the wires through the aircraft and to save weight. This practice means more conductors that need to be monitored for faults and immediate action taken if a fault occurs. In order to protect the aircraft and its occupants should a failure of the major current-carrying wires occur, a fault system is installed. One system protects the battery wiring, while an entirely independent system protects the generator wiring. Even though the battery and each generator's fault control system are totally independent, they use similar components and work on the exact same principle. Let's look at this simplified schematic to explain their operation. As the name implies, feeder fault protection, the system is designed for that very purpose. Those of us familiar with fluids and plumbing know that when you have a leak, you have a mess. The problems with electric current is that a leak can lead to disastrous results. If a wire that is connected to a source of electrical power comes into direct contact with the aircraft structure, a new electrical circuit is created. Unfortunately, it is a circuit that is not supposed to exist, a leak. When electrical current leaks or shorts to ground, tremendous heat is produced. This heat can damage the aircraft structure and could even lead to a fire. This damage to the structure will continue until the electrical source is disconnected. The feeder fault system is designed to monitor the path of the electricity flowing through the feeder lines. This is a fundamental difference between the fault system and a circuit breaker protected system. A system protected by a circuit breaker is being current monitored. The circuit breaker has a certain rating, say 10 amps. This means it will allow a maximum of 10 amps to flow across the circuit breaker. If the current exceeds this amount, the circuit breaker will open internally and stop the flow of electricity. If a feeder wire downstream of the circuit breaker were to short to the aircraft structure, the circuit is likely to quickly draw more than 10 amps, which will cause the breaker to open. Feeder wires protected by the feeder fault system are being path monitored. This is to ensure that the current flowing at one end of the wire is exactly equal to the current flowing at the other end of the wire. The amount of current flowing through the wire is not considered, just that the amount flowing through both ends of the wire are equal. In a circuit breaker protected circuit, the protection system becomes active when the current flowing through the system exceeds the rating of the circuit breaker. In a fault protection system, the protection system becomes active when the current flowing through the feeder line becomes unequal. Monitoring the total current flow through a circuit is relatively simple, usually requiring a little more than an appropriately sized circuit breaker. Monitoring the path of electricity is a little more complex. In the Merlin and Metro series, the wires being monitored include the main feeder lines from each battery and the main feeder lines from each generator. Components used in the battery feeder fault protection system include the battery fault control box, battery fault transformers, and an annunciator panel light to tell the pilot that the battery fault system has sensed a fault and has automatically disconnected. Components of the generator fault system include circuitry inside of each generator control panel, fault transformers, and a generator fail light. You've probably noticed that the transformers mentioned in both the battery fault system and the generator system are similar in appearance. They are in fact identical, and so for that matter are the entire battery fault and generator fault circuits. They just protect different wires. The path of the wires being monitored is as follows. The wires from each battery positive terminal are routed through the wing through the fuselage, and into the J-box located in the cockpit. The generator wires are routed through each nacelle, through the wing center section, through the fuselage, and into the cockpit J-box. From the J-box, power is distributed to each bus of the aircraft. While we're discussing the routing of major electrical feeder wires, the installations in the right-hand nacelle are worth mentioning. This group of electrical components distributes electrical current to be used during engine start. Each source of electrical power must also provide a means for electricity to return. This is accomplished by connecting the negative side of each power source to the aircraft structure. Here is a ground connection for the left-hand generator and battery. Here is the ground connection for the right-hand generator and battery.
Working with the DC power and distribution system requires DC sources. For maintenance purposes, you can use an APU, but that can't easily be connected to the battery or generator wiring, and therefore makes troubleshooting these systems difficult. In the case of the battery fault system, it can't be tested unless the generators are operating and on the line. At the factory, these needs are provided through some additional ground support equipment. This is a large roll-around battery made from non-flight-worthy battery cells and battery pieces. It can be connected directly to each battery connector. Electrical motor-driven generators are connected in place of the real generator. Power output must be limited because of the size of the electric motor. The generators are, of course, unairworthy, and most of the rest of the parts were found surplus, so the total cost was low. Using these devices allows the battery and generator control systems and the battery and generator fault systems to be thoroughly tested in the hangar. Now let's return to our program and talk about the fault detection system itself.
It should be obvious that quite a bit of high current carrying feeder wiring is routed through the aircraft. Remember, the fault system must monitor all of this wiring and take quick and immediate action should a short to ground occur. To explain the system itself, let's use a typical high current feeder circuit. Shown here are the major current carrying wires of one of the engine-driven starter generators. There are also high current carrying wires connected to the generator for starting purposes, but for clarity these wires have been omitted. The output of the generator is routed to the J-box installed in the cockpit. The negative side of the generator is connected to the aircraft structure. From the J-box, power is routed to the respective bus, where individual circuit breakers feed the individual systems. Each system itself is connected to ground, so there is a return path for the electrical current. We will install ammeters at each end of the generator wiring to be monitored. Let's call the ground side point A and the J-box side point B. Now at any given time, the reading of the ammeter at point A must equal the reading of the ammeter at point B. Think of the ground side connection as the return and the J-box side as a distribution point. If the system is operating properly, no more could be returning than is being distributed. Now suppose the ammeter at point A did read higher, say twice as much. What condition could make such a reading possible? Remember, our ammeter at point A always shows what is returning from the system. The ammeter at point B shows what is being properly distributed by the circuit. If A is greater than B, then some amount of electricity must be flowing through a path never intended, a short or leak in the system. Using meters to illustrate the actual operation of fault detection system is fine, but meters would never be satisfactory for use in the aircraft. Someone would have to watch them constantly for the evidence of a fault, and then manually disconnect the source of power to the malfunctioning circuit. With the destructive potential of high electrical currents, speed in the detection and isolation process is essential. The feeder fault system uses detectors instead of ammeters. These detectors are called transformers and use a property of electricity we discussed briefly in our previous program. Let's now apply some loads to our system and discuss the operation. If the pilot operates a system on board the aircraft, say windshield heat, the current being provided by the generator system will increase. This increase will be indicated by both of our ammeters. When the current increased, the small electrical field that surrounds a wire carrying electricity increased as well. If we were holding the current carrying wire in our hand at the time the current flowing through it increased, we would feel nothing. But the transformers installed at the return and distribution side of a feeder circuit would. Each time the current flow increases in the system, a very small amount of current flow is induced into each transformer. This current is detectable at the output of each transformer, labeled with the connections X1 and X2. Now let's analyze the operation of these components together. An additional load is applied to the bus. Both ammeters' readings will increase to reflect this new level of electrical use. At the time the new load was applied to the bus, a small signal would have been generated by each fault transformer. As long as the current flow through the feeder system was correct, the signal created by the fault transformers will be exactly equal. These signals created by the fault transformers have a polarity, that is, a positive and a negative output. If we connect them in opposition to each other, that is, plus to minus and minus to plus, and the signal they are each producing is equal, the results will totally cancel each other out. In fact, when the feeder circuit is working properly, this is exactly what the fault transformer system should show, nothing, or equilibrium. Now let's try our other scenario, an electrical leak in the system. When the leak occurs, the total flow of current through the circuit will increase. Ammeter A will see it. The fault transformer installed next to ammeter A will sense it. Ammeter B and its fault transformer will not. They are being bypassed in the current flow process. Now, no matter how the transformers are connected, there will be a signal created, because B cannot possibly cancel out A. Monitoring the resulting signals from the fault transformers are additional electric components. In the case of the battery fault system, these components are installed in the battery fault box. In the case of the generator systems, the components are installed in the generator control unit. In every major source of electrical current, there is a large relay installed very close to the source that can be used to disconnect it from the aircraft wiring. The control of this relay is usually shared by the pilot and the fault system. The pilot, through switches in the cockpit, can connect the source to the aircraft wiring, but the fault system circuitry can also disconnect the source. When the fault system senses that there is an output from the fault transformers, that their outputs have not canceled each other, it will disconnect the source from the aircraft wiring.
Well, that just about covers our overall view of the DC distribution and control system. Now, before we end this program, we'd like to cover one more item in a little more detail than we normally do. The fault circuit on these aircraft has been the source of many maintenance problems in the field. Unfortunately, a large percentage of these problems were caused because mechanics simply did not understand the system. When we have a situation like that, we'll go into more detail than normal. Our next segment discusses some of the inner workings of the fault control circuitry. We'll give the same kind of in-depth coverage to the other systems of the aircraft that have been identified as frequent troublemakers.
In our previous discussion of the battery and generator fault circuits, we spoke of circuitry that monitors the output of the pairs of fault transformers and reacts when an imbalance is sensed by disconnecting the electrical source. These components are located inside of electronic boxes that a mechanic would not disassemble or repair in the field, so their precise operation is not important. But as an aid to understanding and troubleshooting the system, we're going to discuss their general operation. Here's a simplified schematic, the components of the battery and generator fault systems. Our two transformers are shown at opposite ends of the wires being monitored. Notice that the transformers are connected to each other at one end and to several diodes at the other. The transformers have been connected in a way that the polarity, or direction of output from each transformer, is opposite. This causes the output of one transformer to cancel the output of the other transformer if their outputs are exactly equal. Also connected to the transformers are four diodes, arranged to form what is called a diode bridge. Remember that the diode allows current flow in one direction only, the direction indicated by the part of the symbol that resembles an arrow. The current from our transformers will cross this diode bridge and flow to another device called a signal controlled rectifier, or SCR for short. An SCR looks a lot like a diode, and it acts like a diode with an important difference. It always blocks the flow of current in one direction, just like a diode. But it doesn't allow current flow in the other direction either, unless it is told to do so. We tell it to do so by supplying a small amount of voltage through another connection to the device. When this voltage is present, the SCR turns on and allows current flow. In our example, we see that the SCR is part of a relay circuit. Power is supplied to the relay coil, but it can't flow through the coil and energize the relay unless the SCR has turned on. If the SCR is turned off, as is shown here, the relay will be relaxed. We can use the closed contacts of the relay as part of another circuit that controls one of our sources of electrical power. If the relay is energized, the contacts are broken, and the circuit being controlled will be turned off or disconnected, depending on how it has been designed. For our example, let's say that the circuit being controlled is the connection of the batteries to the aircraft's wiring system, and that the wires being monitored by the fault system are the wires that connect the batteries to the wiring system. When we try and connect the batteries to the aircraft electrical system, the fault detection relay is relaxed, and therefore the circuit can be completed. Current begins to flow from the batteries through their wiring and to the various aircraft systems. If the battery wiring were to short to the aircraft at some point, an output current would be produced by the transformers. This current would travel across the diode bridge and to the SCR. There, this current flow, even though very small, would cause the SCR to turn on and conduct. Current will now flow through the relay coil, which will cause the relay to energize. This will break the contacts within the relay. Once its connection is broken, the circuit the fault system is controlling, in this case the batteries themselves, will also de-energize and disconnect itself. This entire process, of course, happens extremely fast. In fact, it happens fast enough to prevent damage to the aircraft structure should an actual fault occur.
Well, that does it for part one of the DC power and distribution system. In part two, we'll discuss battery control in more detail and talk about some of the more common problems that occur with this system. In the meantime, good flying and good maintenance.